Okay, everybody, this is week 6 for the linear algebra course, and we will continue with the properties of the determinant. Okay, now let's look at the first property of today. Okay, so we see that for an upper triangular or a lower triangular matrix, its determinant is equal to the product of the diagonal entries of the matrix. Okay. So let me remind you what a triangular matrix is. So there were two kinds, if you remember. There's an upper triangular form and a lower triangular form. So for an upper triangular matrix, the entries below this diagonal are all zeros. Okay, and these can be any numbers. Okay, so I put an asterisk here to denote any number. They can be 0 or non-zero. And similarly, for a lower triangular matrix, the elements above the diagonal are all zeros. Okay, so if you look at, for example, determinant of this matrix, we see that it's the product of these three numbers, a, b, and c, the entries on its diagonal. Why? So let's check, let's remember the Sarus rule. So how does it work? So we write the first column, then we write the second column and the third column, and then we repeat the first column and then the second column, right? So if we do this, okay, so these terms are multiplied and they come with a positive sign, and these terms are multiplied, they come with a plus sign, and these come with a plus sign. Okay, so, and let's look at the other direction. So we multiply these terms and they come with a minus sign, and a minus sign. So if you look at it, the only term which is non-zero here is this one, right? Because the others all contain a zero, so they will give zero contribution. Okay, and the similar thing is true for lower triangular matrices. Okay, so I just demonstrated this for 3 by 3 matrices, but this holds for general n by n matrices as well. So if you have a matrix, n by n matrix, which is an upper triangular matrix or lower triangular matrix, is determined as simply the product of entries on its diagonal. Okay, now let's look at this example. Okay, so let's look at this example. So when you first look at it, it looks like a triangular matrix, but this is not a triangular matrix. Okay, so the triangular matrix is a matrix for which the entries below its main diagonal are all zeros, or the entries below its main diagonal are all zeros. For this matrix, none of these conditions hold, so this is not a triangular matrix. Okay, so but we can easily convert this matrix to a triangular form. How do we do that? So if we just swap these two rows, row 1 and row 3, then the matrix becomes a triangular matrix. And if you remember from last time, swapping two rows changes determinant by a product of -1. So we can write this like this. So this is equal to -1 times. So I'm swapping the row 1 and row 3. 0, 0, 5, 2, 0, and 3, 4, 5. Okay, now this is a lower triangular matrix because the entries above the diagonal, these three guys, are zeros. So it's easy to compute the determinant of this matrix. This is simply, so there's a -1 here, another -1 coming from this term, and then we have product 2 and 5. So the answer is 10. Okay, so in the last lecture we have seen that determinant of a matrix is equal to the determinant of its transpose, right? So this justifies the fact that the column operations can also be used instead of row operations when computing a determinant. What I mean by this is, uh, so we have seen that if we swap two rows, then the determinant is multiplied by a negative sign. But we can do this also for columns. So swapping two columns, column I and column J for different columns, makes, when you do this, you multiply the determinant by -1, right? So another property, second property, so this is an elementary column operation. So if I multiply column I by the number k, then I also multiply the determinant by that number k. And the final operation is if I multiply a column by a number and edit the column I, and replace it with column I, then the determinant does not change. Okay, so the same identities regarding the row operations also hold for column operations. So let's apply this uh, in this example. Okay, so we're going to try to compute the determinant of this matrix. Okay, so what do we see? Okay, when we look at it, we see that this column uh, and this column, so the second column is really twice the first column. Okay, so if we do this column operation, which is multiplying the first column by -2 and then adding it to the second column and replacing it with the second column, what do we get? So we get, if we do that, we get 3, 4, -1, and then 0, 0, 0, and then 5, 0, and 1. Okay, so we get a column which is consisting of only zeros. So we have seen that this will give us 0 determinant. Okay, so this equals 0. Okay, let's now talk about a technique which is known as computing the determinant by reducing to triangular form. Okay, so this is very similar to bringing a matrix to row echelon form we have seen in the class. Okay, now let's try to compute this determinant. So I know that we can compute this by Sarus rule, but what I will show you here is more general, and it can be applied for not just 3 by 3 matrices, but any n by n matrix. Okay, so so we start with trying to bring this kind of row echelon form. So I repeated the matrix here, the determinant. So by elementary row operations, I know that this is 2 times, so I'm replacing the first row by half of the first row. Okay, so the other rows are not changed. Okay, so we talked about this row operation. Now I want to make this entry 0. Okay, how do I do that? Well, I multiply this first row by -1 and add it to the third row and replace it with the third row. So if I do that, what do I get? Let me see. So there's 2 here, there's 1, 2, and 3 here, there's 0, 1, and 2, and finally I get 0 here. So -2 times 2, -4, and this is -7, and then -2 times 3 plus 1 is -5, right? Okay, so the last step is using the second row to make this entry 0. So how do I do that? So I write 2, 1, the first row, that will not change, the second row will not change. Now I'm multiplying, you see, the second row by +7 and adding it to the third row and replacing with the third row to make this entry 0. Okay, So if I do that, I get 0 here and 0 here. Now 7 times 2 is 14, minus 5 is 9, and I get this. Okay, at this step, this is a triangular matrix, an upper triangular matrix, so its determinant is a product of entries on the diagonal, okay, which is 18. So you see, during these operations, when I multiply a row by a number and add it to another row and replace it with that row, the determinant does not change. Okay, this is a important property that you should not forget. Okay, now let's talk about the determinant of elementary matrices. Okay, so what are elementary matrices? Elementary matrices are um, matrices which are obtained by doing elementary row operations on the identity matrix. Okay, so these are since the identity matrix has determinant 1, swapping two rows of identity gives a determinant of -1, because we have seen that swapping row uh, is when swapping rows, you multiply the determinant by -1. Okay, and similarly for the second type of elementary row operation, you get a determinant of k, and for the last one you get a determinant of 1. Okay, so let me just give an example regarding 2 by 2 case. Okay, so let's write down, let me choose this one. So this is 2 by 2 identity, and we know that its determinant is just 1. So if I swap row 1 and row 2, then I get this matrix 0 1 1 0, and its determinant is given by the first rule above, which is -1. Okay, and for this, let's look at the second rule. For example, identity, for example, if I multiply the first row by 2 and replace it with row 1, then I get 2 0 0 1, and the determinant of this guy is product of its entries on the diagonal, which is 2. Okay, let us now talk about a lemma which will be useful in the upcoming results. Okay, so the lemma says if E is an elementary matrix, then determinant of E and any matrix A is equal to determinant of E times determinant of A. So how do we show this result? Well, we look at each type of elementary matrix. For example, the elementary matrix obtained by swapping two rows, right? So if I compute this matrix, this is the same matrix A for which row I and row J are swapped. Okay, so then this means determinant of E times A equals minus determinant of A. Why? Because the only thing I did on the matrix A is swapping its two rows, which makes the determinant being multiplied by -1. Okay, but on the other hand, we know that this matrix has determinant -1. Why? Because uh, we have seen this in the previous slide, right? So this is -1 and this is determinant A, so this is minus determinant A. So both sides are equal, okay? And this is also true for other types of elementary matrices. Okay, let me just give you an example regarding this thing that we did here. Um, so let's take 2 by 2 case. Okay, let me make this smaller. Okay, so we have 2 by 2 identity matrix 1 0 0 1, and let us take E to be the matrix, elementary matrix, where row 1 and row 2 of the identity are swapped, which makes it 0 1 and 1 0. Okay, Okay, so now let's take any matrix A, which is A, B, C, D. Then what is E times A? Well, we have seen this. E times A is simply the matrix A where row 1 and row 2 are swept. You can check this, okay? You can check this. So, which means the determinant of E times A will be negative determinant of A. But this is also equal to determinant of E times determinant of A. Why? Well, because determinant of E is, let me use a different color. Determinant of A is simply, determinant of E is simply, I'm sorry, it's minus 1. Okay? Okay, so now let's look at the second result here, um, which says that if B is a matrix which is row equivalent to A, then determinant A is non-zero if and only if determinant B is non-zero. So what does it mean? It means that uh, if two matrices are row equivalent, like A and B, then either both have zero determinant or both have non-zero determinant. Okay, so it's not possible for one of them to have zero determinant and the other one to have non-zero determinant. Okay, how do we prove this? Okay, the proof depends on an idea we have seen a couple of classes before, which says that if B is row equivalent to A, then there exists elementary matrices E1 to EK, such that B is a product of these matrices times A. Okay, so we did this a couple of classes ago, so I won't repeat that here. Uh, okay, now let's use this idea. I know that if I have the determinant of an elementary matrix times another matrix, I can separate them in this way. Okay, so how do we do that? Now, this is an elementary matrix and this is another matrix. Okay, so I can separate this into two parts, one with this determinant and the other with this determinant. Now I can repeat this procedure for ek minus 1 and dot 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 for all till E1, and I get this identity. Okay, so now I know that none of these elementary matrices have zero determinant. Okay, we have seen this in the previous slide. So if we go back, so first type of elementary matrix always has determinant minus 1. The third one has always 1. And the second one has k. And remember, k cannot be 0 here. So k equals 0 is not allowed for the second type of elementary matrix. So if we go back, uh, we have proved this theorem. Okay, so here is a theorem which is very powerful. It characterizes those matrices which are non-singular. So remember what non-singular is. Non-singular matrix means the matrix A has an inverse, okay, has an inverse matrix. So we're answering this question, which matrices have inverse? Well, only those matrices which have determinant non-zero. So this is very important. So its proof is again depending on ideas we have seen before. So if A is non-singular, then it's a product of elementary matrices, and uh, so its determinant is non-zero. On the other hand, if A is singular, then it is row equivalent to a matrix which has a row of zeros, hence its determinant is 0. Okay, now a corollary of this is if A is an n by n matrix, a square matrix, then this equation A times x equals 0 has a non-trivial solution if and only if its determinant is 0. So what does non-trivial solution means? It means that there's a solution x where some of the entries are non-zero. Okay, so if you remember, this equation always has the trivial solution. The trivial solution being the solution where x is all zeros. Okay, 0 0 dot 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 0. So if you put x equals this vector here, then it automatically satisfies this equation. Non-trivial solution means some of the entries here are non-zero. So it says, this corollary says, this is only possible if determinant A is 0. So this is an example, a theoretical example. So we suppose determinant of A is minus 2. So minus 2 has no importance here. It's the only important thing here is it is not 0. Okay, so describe the set of all solutions to the homogeneous system Ax equals 0. Well, according to this corollary above, we see that since determinant is non-zero, this system will have only the trivial solution, okay, the solution that I have written here. And if A is transformed to a reduced row echelon form, then what is this reduced row echelon form? The answer is identity. Okay, and so can this non-homogeneous system can have more than one solution? The answer is no. Why? Because since its determinant is non-zero, it has an inverse, and if I multiply by its inverse from left, from both sides, I get this solution. So there's only one solution. This is the only possible solution. Does the inverse exist? Yes, we have seen this in the previous slide. Okay, so another very powerful theorem about determinant. The determinant of two matrices A and B equals the product of its determinants. Okay, so determinant of A times B equals determinant of A times determinant of B. So how do we show that? So we have two cases. Either A is non-singular, meaning A has an inverse, or A is singular, meaning A does not have an inverse. So if A is non-singular, then we have seen that it can be written as a product of elementary matrices. Okay, so A times B equals this one. And we have seen that we can separate this product into determinants when these E's are elementary matrices. Okay, so we can write it like this. So what is this? Well, this is basically the determinant of A. We have seen this. And so we have proved this identity in the case of non-singular A. And what about singular A? So if A is singular, then we know that it is row equivalent to a matrix which has a row of zeros. So A times B equals some elementary matrices times a matrix which has a row of zeros. Okay, now I can still separate these determinants of elementary matrices, and what is remaining is this part, C times B. Now what is the determinant of this guy? So let's quickly check that this will be 0 for 2 by 2 case. So suppose that our C is something like this, 0 0, okay, and B is anything here. So this is matrix C and this is matrix B. So if I take their products, what do I get? Well, just look at the second row here. Okay, so this one. So if I multiply this row by this column, I will get 0. And if I multiply this row by this column, I will get 0. So CB will always have a row of zeros here, which means its determinant must be 0. Okay, so if A is singular, then we see that this part is 0, which means the identity is satisfied. Okay, why the identity is satisfied? Well, you see, this matrix is, this part is 0, but determinant of A is also 0, right? Because it's a singular matrix. Okay, so Since this determinant is 0, it equals 0, and this part also equals 0, so we're done. Okay, so final property of determinant today is determinant of the inverse matrix, if it exists, of course, is 1 over the determinant of the matrix. So what is the proof? Well, the proof is a matrix multiplied by its inverse is just the identity matrix. So this determinant equals this determinant. But we know that for identity matrix, the determinant is 1. And we have also seen that we can separate determinants like this. Okay, now if I solve this equation for determinant of a minus 1, I get this result, right? Okay, so like a common mistake that students usually make is you can separate products of matrix products when computing determinants, but you cannot do this for matrix sums. Okay, so in general, determinant of a plus b is not equal to determinant a plus determinant of b. So let's see an example of what I said. So let's take, for example, let me make this bigger. So let's take a to be, I don't know, 1, 2, 3, 4, and b to be 0, 1, 3, 5. Then what is determinant of a? Determinant of a is 4 minus 6, which is minus 2. Determinant of b is 0 minus 3, which is minus 3. And what is a plus b? Let's look at a plus b. A plus b is the matrix 1, 3, 6, 9. So determinant of a plus b is 9 minus 18, which is minus 9. Okay, so you see determinant of a plus b is minus 9, but it's not the same as determinant of a plus determinant of b, which is minus 2 minus 3. Okay, so we have to be careful about this fact, okay, here.